Tonight's lesson is on the greenhouse effect, which is section 8.6 in your textbook. The greenhouse effect is related to climate change, but they are not the same, so we need to make sure we understand the difference between the two. First of all, let's see what the greenhouse effect does. Without the greenhouse effect, our average temperature would be around -18 Celsius, but the greenhouse effect warms the Earth's surface by about 33 degrees, which seems like a huge amount, but it brings the average Earth temperature to somewhere around 15 degrees on the plus side, which makes it habitable. At -18 for an average, pretty much everything would die. What's going on is this. There are certain gases in the atmosphere which are able to absorb heat energy from infrared radiation, and when they release it, some of it goes out into space, and some of it is heading back towards the Earth's surface. So the greenhouse effect traps heat energy and re-releases it back towards the Earth's surface. It's totally natural, and everything that's alive on Earth today pretty much is dependent on this in order for us to survive, because we need water to be liquid form in a lot of places to survive. We might notice this more if you notice on a cloudy night the temperature tends to not fall as much. It's because the clouds are good at trapping some of that heat energy, absorb the energy coming up from the Earth's surface, and re-radiate back at us. Moving on in 3, 2, 1. Let's look at the details of what makes up our atmosphere. The gases themselves are nitrogen and oxygen, which represent 78 and 21% of the atmosphere respectively. So mostly nitrogen, a significant amount of oxygen. 78 plus 21 is 99. The remaining roughly 1% are noble gases like argon, neon, and krypton, and that adds up to about 100. These gases absorb almost no infrared radiation, so they do basically nothing for the greenhouse effect. Molecules that have 2 or more bonds. These are the ones that are able to effectively absorb infrared radiation. They're the ones that trap the heat, and we call these molecules greenhouse gases, or GHG, greenhouse gases. The main ones are water vapor, carbon dioxide gas, methane, nitrous oxide or N2O, ozone, and CFCs. What we're going to see shortly is the ozone. It's a pretty small player, so we're not going to concern ourselves with that a great deal. So we're going to focus on the other 5. And moving on in 3, 2, 1. Now, greenhouse gases are not very concentrated. There's not very much of them in the atmosphere because, remember, we added up to basically 100. So they're measured in a very tiny unit called parts per million. Parts per million means grams per liter, or sorry, milligrams per liter. So it's a very, very, very small unit. We're going to make a chart. These are the headings. And so we've got these headings, and there's going to be 4 lines after this. And all the lines are going to either be the symbol for a gas or a number to follow. So don't add beyond the 4 lines below these headings because that's all it's going to take. So the heading plus 4 lines more. So the first column is the gas, meaning which gas are we talking about. CO2 equivalent means how much the gas traps heat compared to CO2. So if a molecule of CO2 traps a certain amount of heat, is another molecule more or less able to as a number? Is it twice as effective? Is it 100 times as effective? How good is it at trapping heat energy? 1800 concentration means what was the concentration of the gas back in 1800? And we know this from trapped gases inside ice cores. What's the concentration today? Again in ppm. The right-hand column says CO2 equivalent increase, meaning when we look at the difference between those 2 concentrations and multiply by the CO2 equivalent, that's how much of a heat trapping ability we have changed in that time. Let's look at the first gas. CO2 obviously has an equivalent trapping ability of 1. Its concentration was 280. It's now 384, which is a jump of 104. So we've seen a pretty significant increase from 280 to 384. That's about a quarter increase, which is a significant increase in the concentration of the gas. Methane, CH4, it's 25 times as effective at trapping heat energy. Its concentration was pretty small at 0.7. It's gone up to 1.8 because we drill for natural gas and some of it leaks out, so we're going to get more. We also get a certain amount from swamps, cattle, things like that, and so there are other contributions, but I think a significant one is the drilling for oil and gas and the cattle. So even though we have only a 1.1 ppm increase, we have a 28 ppm equivalent increase in the heat trapping ability. Nitrous oxide, we get this from lightning strikes and from car exhausts. Concentration back in 1800 was only 0.27, small increase to 0.32, so not a huge increase, but because it's about 300 times as effective at trapping heat as the CO2, it's got an effective increase of 15. So that's a significant increase for a tiny little change in concentration. The last one in our chart is the CFCs. Because there are a variety of CFC molecules, there's a range of 50 to 15,000. At 1800, its concentration was 0 because we make them all, so naturally occurring CFCs is 0. And today's concentration is really small, but because the values are so high at their effectiveness at trapping heat energy, it actually measures up as an 8 ppm increase. CO2 gets a lot of attention in the media, but these other gases, and I'm going to say that we should expect that the methane is going to see the most increase over the next few years. CFCs should be dropping, nitrous oxide should probably be dropping, CO2 is going to go up, but we really got to be careful with that methane because of its CO2 equivalent at 25. Moving on in 3, 2, 1. Now, we didn't talk about water. Water's concentration varies widely based on season, location. It's often under 3%, but we can't control it. We can't change how much evaporates. We can't change how much we breathe out. We can't change how much rain falls out of the sky. It's just impossible to control effectively. A new term is called a sink. I know that comes after water. Sinks are places where a gas can be removed from the atmosphere and stored for a period of time, but it's possible to get it back later. An example would be a forest. A forest acts as a sink for carbon dioxide because the plants take in the carbon dioxide and store it, but later on when the plant dies and rots or when the plant is burned, that carbon dioxide gets re-released into the atmosphere. Moving on in 3, 2, 1. So in class, your seat work is going to be the following. You're going to look at page 342, numbers 1 and 3 to 7. But the other thing we're going to do is we're going to have you rank the greenhouse gases in order of easiest to hardest to control the concentrations. So you're going to have to do a little bit of research, use your phones and figure that out. But we can do all of that in class. And we're going to try and determine a ranking for how well you think we can control each of these gases. And that's our starting point for global warming. We're also going to watch a short movie in class that hopefully helps explain it in a little different way than I do, so that'll help you understand. Thanks for watching.